Good afternoon, everybody. This is Math 2413. It's October the 18th. And today we're going to cover section 4.5 in your textbook. We're going to talk about increasing and decreasing functions, relative maximum and minimum values, and concavity of a graph, and points of inflection. So we've got lots and lots to do today. A couple of announcements before we get started. First of all, the homework for the rest of the semester, that's chapters 4 and 5 homework, is going to be posted during the day today, and I'm on my Google site where the syllabus is. I'm also going to email everybody sometime during the day today also and send that out as an attachment. And so that'll have homeworks 4, 5, and 6 on it, and all the homework from chapters 4 and 5. So be looking forward to getting that document. Next week is a test week, or beginning of a test week at least, and so we have some changes to make sure that you're aware of. Monday of next week, we have lecture as usual, and we're going to continue talking about graphs of functions and how it relates to derivatives. And then on Wednesday, no lecture on Wednesday. Make sure we are all aware of that we will not have live lecture next Wednesday. I will be on campus next week for on-campus hours on October the 24th on Tuesday from 4 to 6 p.m. And on Wednesday, the hours on Wednesday are a little bit iffy right now, but right now I'm going to say 11 a.m. to 1 p.m. It's possible it could be a little bit earlier, definitely possible it could be a little bit later than that. And I'll be emailing you about when those exact times are for next Wednesday. Remember that I have online office hours, and those online office hours are tonight. So that's Wednesday from 8 to 9 p.m. And then tomorrow from 1 to 2 p.m., so that's Thursday, 1 to 2 p.m. And then on Sunday from 7:30 to 9 p.m. So don't hesitate to come by my office if you have questions, my online office, if you have some questions about homework problems and such. Remember that Exam 2's testing window. So Exam 2, the window opens October the 26th and runs through October the 31st. So that opens next Thursday, October the 26th, then goes through the 31st. The review for Exam 2 is posted, and on my Google site, very good review, lots and lots of problems, longer than your test is going to be, but a really good review to look at. It's not just problems out of the textbook like Exam 1 review was. These are actual problems that I've made up and put up on the on this review, and you'll also have a separate document that has all the answers to that as well. Please start working on that and getting yourself together as far as getting ready for Exam 2. And I would spend some of this weekend getting ready for that and starting to think about how you're going to prepare for Exam 2. All right, the material for Exam 2 stops with what we do today. And so today we're going to talk about increasing, decreasing functions, relative maxes and mins, and concavity and points of inflection. So let's go ahead and get started. I have a couple of graphs on this next page. Here we're talking about F increasing and F decreasing, and some pictures here. And so I want to look at these pictures and talk about how this connects to the derivative. So the first three pictures are all pictures of a graph that's an increasing graph. And because the graph is increasing, the slopes of the tangent lines are all positive in those pictures, right? No matter where you are, and probably easier to draw on the second and third graphs than on the line, but you have tangent lines that maybe look like this on these first graphs. These are all sloped positively. And so what do we know here? And that's certainly true in the first picture also. We know that on all these, the slopes of the tangents are all positive. And so what do we see? That in each of those pictures, we can definitely see that f prime of x over the interval from a to b, certainly f prime of x is positive. F prime of x is going to be positive in that interval from a to b for sure there. From a to b, f prime of x is going to be positive in this picture. And even though the third one is shaped differently than the first one, those are both rising graphs. The y value is getting bigger as the x value is getting bigger. And so certainly it's going to be true that f prime of x is going to be positive in the interval from a to b on that graph also. The derivative is always positive in the interval from a to b for all three of those graphs. And so you can see at the very bottom of the page, I've got f increasing on AB when, and what we could do is we could finish that punchline by saying when f prime of x is greater than 0 for all x in the interval from a to b. Right? If the derivative is positive everywhere in that interval, then that function is going to be increasing on that interval. In the second picture, we have that the slopes of the tangents are all slanted, or that the tangents themselves, I should say, are all slanted downwards, no matter where you draw these. And because those are all slanted downwards, we know that the slopes of the tangents are all negative. And so what do we know? That on the interval from a to b, in the first picture, f prime of x is always negative. And on the second picture, even though the shape of the graph is different, the graph is still falling. The y values are getting smaller as the x values are getting bigger. And so on the interval from a to b, f prime of x is negative there. And on the interval from a to b, f prime of x is negative on that picture also, even though those graphs are really shaped differently. So we can finish the punchline at the very bottom. We've got f decreasing on the interval from a to b when f prime of x is always less than 0 for all x in the interval from a to b. Right, so we've got to start establishing this connection that the derivative being positive is connected to the function increasing, right? And so I think probably worth going ahead and highlighting that, right? That if f is increasing is connected to f prime of x being positive. And f prime of x is decreasing is connected to f prime of x being negative, the derivative being negative. All right, so very important to kind of establish that connection. Positive derivatives, function's increasing. Negative derivatives, the function is decreasing. All right, so now let's talk about the shape of the graph a little bit. So I've got the same exact pictures on this next page. And so we're going to talk about the shape of the graph. And what I want you to notice on the first graph, actually the second graph in that first group of 3 there, if you look at these tangent lines right here, notice these tangent lines to this graph have increasing slopes. And so what has got to be true is, on this first picture, is that f prime of x is increasing, because the slopes are getting bigger and bigger and bigger. On the other hand, on the next picture, if you look at these slopes, for these tangent lines, as you move along on the second graph there, what's happening there, the slopes are getting smaller. The graph, as you move from left to right, the numbers that describe the slopes are getting to be smaller and smaller numbers, and so you say that f prime is decreasing right there. Well, when f prime of x is increasing, then its derivative must be positive. So its derivative is the second derivative. And so the second derivative must be greater than 0 there. And if f prime is decreasing, then we say that then we know, based on what we talked about on the last screen, that its derivative has to be negative. Its derivative is the second derivative. And so that has got to be less than 0. Functions where f prime is increasing, or the second derivative is positive are called concave up. So this first picture, the middle picture in that first group of three, is a picture of a graph that's concave up. When the derivative is decreasing or the second derivative is negative, then we say that the function is concave down. So notice on this first picture, we've got a function that we've got the function f is increasing. Now be careful. This is f is increasing that I'm writing at the very top right here. Right? So if f is increasing, and f prime is increasing there also, right? Both of those are increasing. This function is concave up. Right, on the next picture, what's true? The function f is still increasing. Right, the function itself is of an increasing function. But now what's its derivative doing? Its derivative is decreasing for that picture. Right, and so when you have a function that is increasing, it's rising graph, but its derivative is decreasing, then you're going to get a shape like we have pictured right there, and you've got that the graph is concave down. Now, on the first picture, that graph is neither, when you have a line, you have a graph that's neither concave up or concave down. Neither concave up or concave down. And what do we know about a line? We know on a line that the second derivative of a linear function is 0, right? So that means the derivative is neither increasing nor decreasing. The derivative we know is a constant in that case, right? So the derivative is constant. And probably not a bad idea to write that down, that f prime is constant right here. Because we know that the slope of the tangent's the same everywhere for a line like that. All right, so going back through those pictures again, we have that if f prime is increasing, then you have that the second derivative has got to be positive, and the function is concave up. On the other hand, if f prime is decreasing, then the second derivative has got to be negative, and the function is concave down. And you can look at the shapes to see about how the bend in the graph would work when you've got a function that's concave up and one that's concave down. All right. By the way, sometimes you'll hear people talk about that a function's concave up when its tangent lines are underneath the curve. Tangent lines are underneath the curve. Tangents are below the curve. And a function is concave down when the tangent lines are above the curve. All right, so now let's look at the next group of graphs. Now in the next group of graphs, the first graph is still a line. The function is a decreasing. All three of these are decreasing graphs, right? F is decreasing in all three of them. The function f is decreasing in all three of them. But let's look at the concavity. So in this first one, f prime is constant again, right? The derivative never changes for a line. And so this one's neither concave up or down. On the second graph, what do we have? We have that it is certainly the case that, see, I'm going to put this maybe in a different color to see if it'll stand out a little bit. We've got that f itself is decreasing. And what do we see about the derivatives? Well, the derivatives are, if you look at the way these tangent lines are slanted, they're all slanted down, they're all negative, but they're getting to be bigger and bigger negative numbers as you move from left to right. Because they're getting to be bigger and bigger negative numbers, they are decreasing. And so we say in this picture that f prime is decreasing. If f prime is decreasing, then the second derivative must be negative. And so what do we have here? That this function is concave down also. Right, so this one's concave down. This middle picture is concave down. In the first group of graphs, it was the third picture that was concave down. All right, and then in the third picture, what do we have here? That these tangent lines, if you look at the tangent lines, these are all slanted down still, but now they're getting to be more shallow. They're all negative slopes, but the numbers themselves are getting smaller and smaller. And so they're getting bigger, right? -5, -2, -1, -1/2, -1/3. Those numbers are getting bigger. And so we have here that f prime is increasing, right? The tangent slopes are getting bigger. So f prime is increasing. And so its derivative must be positive. The second derivative has got to be positive. And so we get a function that is concave up. Right, so that's a picture of a function that's decreasing. F is decreasing there, but it's concave up. So f is decreasing, but the function is concave up. And notice what we said in the first group of pictures about the tangent lines. When the tangent lines are below the curve, you get a function that's concave up. Right, so that would be the middle picture in the first group and the third picture in the last group. And when the tangent lines sit below the curve, then, or when they sit above the curve rather, then it's concave down. All right, so at the very bottom, let's fill in the punchlines there. F is concave up on an interval AB when we've seen two ways that it might look up above, but it's the same thing in both of them. When the second derivative of the function is positive for all x in the interval. Right? When you get a positive second derivative, the function is going to be concave up. And the function's concave down when on an interval from a to b when the second derivative is negative for all x in the interval from a to b. All right, so let's kind of look at some pictures here, some kind of putting a few things together here. So let's look at a graph that's shaped like this. All right, so if we're talking about what's happening with the derivative and the second derivative, and increasing and decreasing and all that. So at this value right here at a, what do we have? That the function has a horizontal tangent line. So f prime at a for this function is going to be 0. This is the graph of the function f right here. All right, and then what do we have before a? From -∞ to a in this interval, we have that the function is increasing, so f is increasing in that interval. Right, the function's rising, and so what do we know? Its first derivative has to be positive in that interval. And, right, if function's increasing, first derivative's positive. And what else do we see? That the tangent lines lie above the graph. So this function is, f is concave down. And so what do we see? That the second derivative there must be negative. Now what happens when, with an increasing and decreasing, what happens at a? At a, you get a change, don't you? And at a, the function goes from increasing to decreasing. And so now f is decreasing right here. And so its derivative must be negative in that interval. So that would be from a to infinity. And then the concavity, well, the concavity has not changed. So no change in the concavity at all. The function continues to be concave down. The tangent lines continue to lie above the graph, and so there's no change in the concavity at all at that value a right there. Since there is a change in the graph from increasing to decreasing at a, we say that the function has a relative maximum at a f of a. And actually, technically, f of a is the maximum value, and it occurs when x is equal to a. This point is what we call a relative maximum right here. All right, and actually, technically, an absolute maximum here also, but we're not worried about absolute maxes and mins at this point. We're just worried more about trying to deal with relative maxes and mins. All right, so let's look at another picture. So that function was concave down the entire way. And by the way, if we looked at that same graph again, here's a right here. So we've got this exact same graph, something like that. What we might say here is that what does f prime do? F prime is positive until you get to a, then at a it's 0, and then f prime is negative afterwards. Right? The function's rising and then it's falling. So its derivative goes from positive to negative. And then its second derivative, well, the function is concave down through the entire interval, and so the second derivative is always negative in that interval. There's no change in its second derivative sign anywhere in there. All right? And so now what we're going to do is we're going to look at different pictures and kind of different features of graphs and kind of analyze what's happening with the graph there. Then I kind of put it all together, and then we'll look at some equations and do the same thing with equations. All right, so in this graph, so now let's say we have a shape like this, and this is the value a right here. Then what can we see? That the graph is decreasing, right, as you go from negative infinity to a in this interval right here, right, the function is decreasing. And since it's decreasing, its derivative must be negative. And then at a, what happens, the graph changes at a. You do get that f prime of a is 0 again. And then at what happens when you go past a, now the function changes to an increasing graph. And so we see that the derivative must be positive like that. Right? And then what about the concavity? Well, the concavity of this function is concave up everywhere throughout this entire interval. The concavity doesn't change, so it's always concave up. And because there's a change in the derivative from negative to positive here, and because the graph goes from falling to rising or decreasing to increasing, we have a relative minimum at a f of a. Right? And if we look at the exact same graph, kind of analyze the signs, we have a graph that kind of looks like this. Like so, what do we see? That this is the graph of f. Remember, in both cases, that you always have to pay attention to what you've got the graph of, whether it's a graph of f or the graph of f prime. In this case, what's happening to the derivative? The derivative is negative, and then at a it's 0, and then the derivative changes to positive because the function goes from rising to fall, or from falling to rising, or decreasing to increasing. And then what about the second derivative here? Well, the second derivative is concave concave up. So the second derivative, sorry, I'm going to put the signs there. That's what I should have been doing. So let me erase that real quick. And so the second derivative is just always going to be positive in this case. Right, everywhere in there it's going to be positive because the function is concave up. And again, look at the tangent lines if you want to throughout this picture. Right, what about the tangent lines? The tangent lines sit below the graph. So when the tangent lines are below the graph, it is concave up. In the previous picture, what do you have here? That the tangent lines lie above the graph right here. And so this graph is going to be concave down, like that. All right? All right, so let's see. Let's continue to move on to some different ways a graph might be shaped and talk about what's happening at those points and what is happening to the first and second derivative at these points. So if we have a graph like this, so let's say we have a graph that's shaped like this one right here, and I tell you, I don't want to go that far. We'll just make it look like, actually extend that value a little bit. I'll get it right. All right, so we're going to have a graph that looks like this one right here. So what's going on in this particular case? We can kind of streamline this process. The graph is going from, at A, what's it doing? It's going from increasing to decreasing. So what do we have? That the derivative must be, remember this is the graph of f here, the derivative is positive in this interval, and the derivative is negative in this interval. And then what about the concavity? Well, the concavity of the function is going to be up, and concavity here is still up. All right, so what do we have as far as signs go for this? Then you could say that f prime is positive until you get to A. And now what's happening here? There's a vertical tangent at this point. Remember, this is called a cusp. And so we have a vertical tangent there. That's called a cusp. And in that case, the derivative is actually undefined. All right, so f prime at A in this case does not exist. It's undefined. And so we could say does not exist right here for the derivative. And then what happens? The derivative changes to negative because the function starts to decrease. What's still the case here? The derivative changed from positive to negative. Function changed from increasing to decreasing. And so there's still a relative maximum at a f of A. Still have a relative max there. All right, now what's happening to the second derivative? Well, there's no sign change in the second derivative. It's concave up, and it's still concave up. Now what happens here is that when the first derivative is negative, the second derivative is going to be negative. When the first derivative does not exist, the second derivative is not going to exist either. And so the second derivative is going to be undefined at A in this particular case as well. All right, so we have a function that went from increasing to decreasing, but we looked at the concavity, so we're talking about what's going on with a cusp there. All right, the next picture we want to look at. Let's look at this graph. I'm going to go ahead and maybe put this one in red right here. So we have a graph that looks like this. Now, it doesn't look like a lot's happening here. There's certainly no relative maxes or mins just based on the way the picture looks. But let's look at what's happening as the function's increasing and decreasing and everything. So here's A right here. And what do we have? That the function's increasing until you get to A, and then but it's still increasing after A. So what do we have here? That the derivative of this function, remember this is the graph of the function f, the derivative must be positive here. It must be positive when you're bigger than a also, because the function's always increasing. But what's certainly true here, there's a horizontal tangent line right here at that point. So you have a horizontal tangent there. And so what do we know? That f prime at a is equal to 0. And then what about the concavity of the function? Well, this function is to the left of a is concave down, right? The tangent lines lie above that graph. The derivative is getting smaller. And after a, the function is concave up. So this one has a change in the concavity at x equals a. That point, when you get a change in concavity, when the concavity changes, that kind of point is called a point of inflection. And because of this change in concavity, then we have a point of inflection at a f of a. All right, and then so let's look at the signs of the derivative and the second derivative here. So the derivative, notice, is positive. Function's increasing. At a, you have a horizontal tangent line, so it's 0 there, but then it still stays positive afterwards. The second derivative, on the other hand, we got something different going on here. The second derivative is going to be negative because the function's concave down. And then what happens at a, the second derivative changes sign to positive. Function changes to concave up. Second derivative is going to be 0 at that point, right there. Right? So when you get a concavity change, you've got a function that's going to have a point of inflection at that point. So let's kind of summarize some of that information here. So we've gone through those pictures. So if f goes from increasing and then it changes to decreasing, then what's happening? Then the derivative is going from positive to negative. That's the derivative function. It's changing from positive to negative. And you get a relative maximum when that happens. When the function changes from decreasing to increasing at a point, then the derivative of that function then the derivative of that function changes from negative to positive, and you get a relative minimum. Right? That's when f goes from decreasing to increasing, and then the first derivative is going to change from negative to positive. Right? If, on the other hand, you've got that f is increasing and it doesn't change, it still stays increasing, right? Or the function is decreasing and at a specific point doesn't change and it continues to decrease, then you get no relative extrema at all. No relative max or min at all in that case. All right, and now when can these changes occur? You get changes like this, and we've seen in the previous picture, these the derivative f prime can change from positive to negative or negative to positive when f prime is equal to 0 or f prime does not exist. Right? When one of those two things happen, and remember, those are called the critical numbers for the function. So the critical numbers are places where you could get these relative maxes and mins. That's when the derivative goes from positive to negative. When the derivative changes from positive to negative or changes from negative to positive, it means the function is either going from increasing to decreasing or decreasing to increasing. When can that happen? It can happen when the derivative is 0 or when its derivative is undefined. And those are called the critical numbers. Now notice I put can change. It doesn't have to, because we've seen a picture where it doesn't have to, right? All right. When f is goes from concave up, let's see, so concave up, and it changes to concave down, then what's happening? Then the second derivative goes from positive to negative. Right, the second derivative changes, and you get a point of inflection. And it works the other way the same. If the function changes from concave down, and it changes to concave up, then the second derivative changes from negative to positive. But either way, what do you get? You get a point of inflection. All right, and then finally, if there's no change in the concavity, then you don't get a point of inflection, obviously. When can these things happen? These can happen, sign changes in f double prime can happen, or happen, not can happen, but happen, when the second derivative is 0 or the second derivative does not exist, is undefined. Sometimes I actually refer to those, those places for the first derivative are called critical numbers. For the second derivative, a lot of times we'll call those hypercritical numbers, just to distinguish them. The book we are using, and a lot of books do not use that terminology, but I just use that terminology just to distinguish them. And sometimes I'll just abbreviate that H critical. Call them hypercritical numbers, and those are places where the second derivative is 0 or undefined. All right, so kind of summarizing some things here, and then we're going to look at some other information from graphs and kind of piece together a little bit more complicated versions of all this, and then we'll finish by looking at some equations. So we still have a decent amount to look at here. But if you're given a graph f, given a graph of f, right, if f prime is positive, then f is increasing. F prime is negative in an interval, f is decreasing. If f prime changes from negative to positive, then you've got a function that's going from decreasing to increasing, and that implies a relative minimum. And if f prime goes from positive to negative, it implies the function's going from rising to falling, and that means you have a relative maximum. Right? Places where the first derivative is equal to 0 or where the first derivative does not exist, is undefined, are called critical numbers. And just because you get the derivative to be 0 or the derivative to be undefined, remember, doesn't mean you have a relative max or a min. Just means you could have a relative max or min. All right, and then alongside this, let's go ahead and write the corresponding information about the second derivative. Right? If the second derivative is positive, then f is concave up. If the second derivative is negative, then f is concave down. And if f double prime goes from negative to positive or from positive to negative, either way, then you get a point of inflection. And the places where the second derivative is 0 or where the second derivative does not exist, we're going to call those hypercritical numbers, even though that's not really standard terminology there. All right, so let's look at a picture of some graphs, first of all, and kind of in a couple of different ways we're going to do this, but let's say we've got a graph that looks like this one right here. And let's say this graph looks like this. Comes down like this. This is the graph of the function f. Like so. All right, so if this is the graph of the function f, then let's talk about what's going on with, first of all, the derivative. So what do we have here at 4? What do we get? That f prime of 4 is 0. And this is at 7 right here, and we've got that f prime at 7 is 0, because we're getting horizontal tangent lines at those places. And then this is at 11 right here, then you get that f prime at 11 is 0. Right, and so what about the signs of the derivative? The signs of the derivative are going to be, what does the function do? The function goes from falling, so at 4, so its derivative is going to be negative until you get to 4. It's 0 at 4, and then the derivative is going to be positive after that until you get to 7, and then it's going to be 0 again. And then the graph starts to fall. The derivative is going to be negative until you get to 11, 0 again, and then finally positive afterwards. And so we get these sign changes in the derivative, and so what do we get? We know we have a relative min at 4, 2. We can read the points off the graph the way I sketched it. Then we have a relative maximum. The derivative goes from positive to negative. We have a relative maximum at 7, 5. And then we have another relative minimum. The derivative goes from negative to positive, and this is going to be at the point 11, 3. We have a relative minimum at 11, 3. All right, now let's look at the second derivative. So what's happening with the concavity of this function, and what about the second derivative? So let's just go ahead and write this out. First of all, just in words, and with the second derivative. But as far as the concavity goes, what do we have here? That the graph starts out with a piece that's concave up. But then somewhere right about, and these are harder to pick out, but somewhere right about it where I put that red dot right there, we have a place, and it's 5 point something or other. We'll just say 5.5 approximately, just to use estimates there. So like at 5.5, what do we have? That the second derivative of this graph at 5.5 is going to be 0. And what does the graph do at that point? It changes from concave up to concave down. There's a piece, so this piece right here is concave up. Concave up. And then what happens? Concavity for this little piece right in here changes to down until you get, and probably should, it's a little bit misleading the way I wrote it here, So it changes to concave down until you get to another place where the concavity changes. It looks like it might be right about at this point right in here. We'll say that's at 9. And then what happens after that? Then the function changes to concave up again. So the function changes from concave up and then goes to concave down in between here, and then concave up after that. Again. And so what do we have here? That the second derivative is going to be positive until you get to about 5.5. And then it's going to be 0. And then the second derivative is negative until you get to 9. And then it's 0 again. And then the second derivative is going to be positive afterwards. And what is that? Those signs correspond to where the function is concave up and where the function is concave down. So what do we have here? We write out the relative maxes and mins, the points of inflection. And these would just be estimates. In this case, at about 5.5 and about 3.4, I'd say, from that graph, the way I sketched it. And another one at about 9, about 9.4, we'll say. Right, and those are places where the concavity changes. All right, so let's look at another picture. Look at maybe one more picture, maybe 2 more pictures, and then we'll go from there. All right, so another graph of the function f. This one might be a little bit more complicated. Let's say we have a graph. Let's say this graph looks like this. Comes out like this. There's a cusp here at this point. And then the graph looks like this. All right, so this is definitely a kind of graph that we might encounter. So let's talk first of all about the function increasing and decreasing. So what's happening here? You're going to get a cusp at this value right here, 1, 2, 3, 4, 5. And so what do we have? Until you get to 5, the derivative is going to be positive. And then what happens at 5? Well, the derivative there does not exist. That's a cusp. So there's a vertical tangent line. And then the derivative is negative until you get to 9 right here. Then the derivative is negative. And the derivative there is 0. There's a horizontal tangent line there. And then it appears that the graph continues to rise afterwards. And so this function is just increasing afterwards, like that. And so what do we have here? We have a relative max at 5, 4. A relative minimum at 9, 2. Like that. And those are places where you got a sign change in the derivative. In one place you had that the derivative did not exist, in another place where the derivative was 0. All right, and again, remember this is the graph of the function f. All right, and now the second derivative. So let's have a look at the second derivative. Well, the graph starts out concave up. And then at 5, what happens at that cusp? Well, the graph continues to be concave up afterwards. And it's concave up until you get to right about this point right here, we'll say, which is at 12, 4. And so the second derivative stays positive until you get to 12. And then the second derivative is going to be 0 at that point. And then what happens? The second derivative changes sign to negative. There's only one sign change in the second derivative, and that's at x equals 12. And so what do we have here? We have a point of inflection So a point of inflection at 12.4. Right, and kind of a little analysis of the signs of the first and second derivative for this function right underneath it there. All right, so now let's look at starting with a graph, but this time, this is different, really different. Instead of starting with a graph of f, let's look at the graph of f prime. So this is really different. This is, let's say that we're given the graph of the derivative function. This is the graph of f prime. So now, if you're thinking about when is f, now see, so we're kind of going backwards. What do we do in this picture? We started with a graph of f and we wrote some stuff down about the first and second derivative. On this one, what do? We started with the graph of f, we wrote some stuff down about the first and the second derivative. And all the previous graphs were like that also. So in this one, what are we going to do? We're going to start with f prime, and now we want to write some information down about f. So now, first of all, let's just look at f prime for a minute. Just f prime. Is f prime positive or negative as we're going from left to right? So in other words, is the graph above or below the x-axis? Right? See, so the graph is below the x-axis until you get to 2. At 2, the graph is 0. And then the graph shifts to above the x-axis until you get to, let's see, that was a 2, 3, 4, 5, 6, 7, 8, 9, until you get to 9 right here. And so until you get to 9, and then the derivative is 0 again. And then the graph is below the x-axis until you get to 10, 11, 12, 13 right there, and then it's 0 again, and then it's above after that. So what do we have? That the graph's below the x-axis, above the x-axis, below, and then above. Well, when it's below the x-axis, that means it's negative. And when it's above the x-axis, that means it's positive. And when it's below the x-axis, it's negative, and when it's above the x-axis, it's positive. Now what are those? Those are the signs of the derivative. But if those are the signs of the derivative, then that tells me something about the function itself. It tells me that the function itself is increasing. I'm sorry, whoa, hardly. It's decreasing because its derivative is negative. Whoops, and I probably wrote that word too far, because what happens, this stops at the 2 right there, and then again right here. And then again right here. So that was at 9 right there, and that was at 13 right there. So what do we have? That the graph is decreasing. That's better. Until you get to 2, and then it is increasing when you're between 2 and 9. And then it's decreasing again from 9 to 13. And then it's increasing after that. Okay, so that's a kind of a picture of what the function itself is going to do. So the function itself is going to be falling and then rising and then falling and then rising based on that graph of the derivative. And so notice, what are we going to get here as far as relative maxes and mins? We're going to have a relative minimum at x equals 2. Now, we don't know what the y value is because we don't have the graph of f. We don't have enough information actually to sketch the exact graph of f, because there's lots of graphs that might fit this information. But we do have a relative minimum, we know, at x equals 2, because at x equals 2, the function goes from decreasing to increasing. Now remember, I said the function goes from decreasing to increasing. The picture I have at the top is not of the function. The picture I have at the top is of the derivative of the function. And so when the derivative of the function is negative, I know that the function's when the derivative of the function's graph is below the x-axis, I know the derivative is negative. That tells me the function is decreasing. When the derivative is above the x-axis, it tells me the derivative is positive. It tells me the function is increasing. Right? So we have a relative minimum at x equals 2, a relative maximum at x equals 9, and another relative minimum at x equals 13, like so. Now, I'm not going to do just a huge amount with analyzing the graphs of a derivative like that, but or the derivative graph, but I will want you to take some basic graphs like that and be able to tell me something about the original function. All right, and so now what we're going to do, and probably actually at this point wouldn't be a bad idea to go ahead and look at maybe one more example like that, and then talk. And then after we do one more example like that, then we can go on and look at some equations and try to analyze those graphs. So this is problem this is problem 202 on page 408. So this is page 408, problem number 202. This is section 4.5 of your book. And on that problem, now I'm going to be able to do is kind of reproduce this, kind of rough sketch this graph out. So this graph crosses the x-axis at -2, and then -1, and then at 0 again, and then at 1 again. So it's really kind of crowded in there. And you get this graph of the derivative function. You get that the derivative comes up like this, falls, doesn't actually, it touches the axis but doesn't actually cross there, and then falls again, comes in like this. So this is the graph of f prime. Right, that's not the graph of f, it's the graph of f prime. So what can you tell me about f prime? That f prime is below the x-axis, right, until you get to -2. Right, so the f prime of x is below the x-axis until you get to -2. And then what happens? Now the graph's above from -2 to -1, and then it continues above until you get to 0, and then it's below until you get to 1, and then it's above. Right, so these are the x values that are in play here. You have -2, -1, 0, and 1. And what do you have here? You've got where the graph is. It's the graph of the derivative. It's below the x-axis before -2, less than -2, and then it's above between -2 and -1, and then it continues above until you get to 0, and then it falls below, and then at 1 it crosses back above and is at above again. And what do you have at -2? You certainly have that at -2. F prime at -2 is 0. And F prime at -1 is 0. F prime at 0 is 0. And finally at F prime at 1 is 0. Right? Because that's where the graph of F prime is actually dipping, or is actually crossing the x-axis. Right? So that's all information about F prime. All right, so what does that tell us about, in terms of signs then for the derivative? So we're continuing to talk about f prime here. So the fact that it's below tells me that f prime, let me continue to do this in red right here, that f prime is negative until you get to -2. And then f prime is positive. And then f prime continues to be positive. And then f prime is negative. And that f prime is now positive, right, in those intervals. So what does that do? That tells me something about the graph of the function itself. That tells me something about f. Right? It tells me that when the derivative is negative, that the graph is falling until you get to -2. And then the graph is rising between -2 and -1. It continues to rise between -1 and 0. and then it's falling between 0 and 1, and then after 1 it's rising. All right, you have a nice little picture of what this graph has got to be doing. And so what do we have? That f is decreasing, it's increasing, it's still increasing, it's decreasing, and then it's increasing again. Or if you want to write this out in interval notation, you could, where the function is increasing and decreasing. So let's go from left to right. So from left to right, what do we have? That the graph starts out decreasing, and it starts out decreasing from negative infinity to negative 2. And then from negative 2 to negative 1, the graph is increasing. From negative 1 to 0, the graph continues to be increasing. Now notice I didn't include negative 1 there because at negative 1, we saw that the derivative was 0. So I can't include that value because the derivative is not positive there. All right, so from negative 1 to 0, we have that the function's increasing. And then from 0 to 1, the graph is decreasing. And then finally, from 1 to infinity, the graph is increasing again. In terms of relative maxes and mins, I have a relative maximum at 0, at x equals 0. And that's actually the only relative maximum. And then there's a relative minimum at negative 2, and then another relative minimum at x equals 1. All right, so I was able to tell quite a bit of information from that graph of that function f prime. And so you start out by looking at where f prime is above and below the x-axis. That tells you where the f prime is positive and negative. That tells you where the function is increasing and decreasing. And then that finally will allow you to kind of piece together where there's relative maxes and mins. All right, so now let's look at some equations and talk about some equations and see what we can do to analyze this information. I'm on page 411 of your book. Okay, so page 411, and this is still section 4.5, and we're looking at problem number 226 on that page. Number 226. Okay, so on that problem, let's see, we have this function, f of x equals x to the 4th minus 6x cubed. So what I'm going to do, so when we look at this function, what we're going to do is we're going to analyze it using the first and second derivatives. So I'm going to divide my sheet up into two sections. I'm going to put the first derivative on the left side and the second derivative on the right side. So the first derivative for this function is 4x cubed minus 18x squared. The second derivative for this function would be 12x squared minus 36x. Now what you want to do definitely is you want to factor both of these functions. So f prime factors you can take out of 2x squared. When you take out a 2x squared, you're left with 2x minus 9. And the second derivative for this function, when you factor that out, you can take out a 12x, and you're left with x minus 3. All right, so if you're looking at the critical numbers, you're looking at where f prime of x is equal to 0. And so that would give you x equals 0 and x equals 9/2 from those two factors. And so our critical numbers are at x equals 0 and x equals 9/2. We don't have to worry about the derivative or the second derivative being undefined because these are all polynomials. The second derivative is equal to 0 when x is 0 and when x is 3. And so those are my hypercritical numbers. Hypercritical numbers at 0 and at 3. All right, so we're going to analyze the signs of the derivative here and the second derivative here. We put the critical numbers on my number line, so that's 0 and 9/2. And we put the hypercritical numbers in this number line, that'd be 0 and 3. And then what you're doing is you're going to pick up test values in each of those intervals. So a test value, any number in these intervals works. So like -1 would be a good test value. And x equals 1 would be a good test value right there. And 9/2 is 4.5, so x equals 5 would be fine right there. For the second derivative, test values might be -1 and 1 and 4. Those would all work. All right, so what you're doing is you're literally looking at what the sign of the derivative is at each of these test values. So I'm looking at f prime of -1, f prime at 1, and f prime at 5. And over here, you're looking at f double prime at -1, f double prime at 1, and f double prime at 4. What I would do is I'd look at the factored forms because you get nice little relatively simple factors, and then you can do the arithmetic from there. So like in the first derivative, when you use -1, you get a positive number and then a negative number, so the first derivative is negative. You don't really care what the value of the derivative is, by the way. You just care about what the sign of the derivative is. When you use x equals 1 and put it into the first derivative, you get a positive value and a negative value again, so the derivative is still negative. And then when you use 5, you get a positive, and you get a positive right there. And so that gives you an idea. That tells you where the function is rising and falling, right? It's where the first derivative is negative, the function itself is falling. And then the function still falling from 0 to 9/2, and then it's rising from 9/2 to infinity. So that you get a nice little picture of where the graph's rising and falling, increasing and decreasing. And so what do we get here? That f is increasing from 9/2 to infinity. And then f is decreasing from negative infinity to 0, and then from 0, put a union symbol between these two, a union symbol, and then you get negative infinity to 0, and then 0 to 9/2. Like that, and that's where f is decreasing. Do not include 0 in there because the derivative at 0 is 0, and so it's not decreasing at 0. You have a horizontal tangent line there at 0. Relative maximums, there isn't a relative maximum, so none. And relative minimum would be when x is 9/2 or 4.5, and then you're finding f of 9/2 or 4.5. Figuring out what that is. So let's see, on my calculator really quickly here, I've got 4.5 raised to the 4th power minus 6 times 4.5 raised to the 3rd power, and I get a negative 136.6875 as a decimal. So negative 136.6875. All right, that's my y value. All right, so now let's finish up our analysis of the second derivative. So f double prime at -1. Now you're going to the second derivative and analyzing the signs of the second derivative. Again, I'm looking at the factored form, 12x times x minus 3. So when x is -1, you get the first factor is negative and the second factor is negative, so the second derivative is positive. At x equals 1, the second derivative is going to be a positive and a negative, and so you get a negative. And then at x equals 4, you get a positive and a positive, and so the second derivative is positive. So this tells you where the function's concave up and where the function's concave down. Right? The second derivative is positive, you get a function that's concave up. When the second derivative is negative, you get a function that's concave down. So kind of summarizing that information, F is concave up. When you go from negative infinity to 0, and then from 3 to infinity. And F is concave down when you go from 0 to 3. And then points of inflection, there are 2 of them because there's 2 places where the concavity changes. One place is at 0, and so you get, and remember, you're going to the original function when you're evaluating here. So you have 0, and then that's easy, the y value 0. The other one is when x is 3, and the y value there would be 3 to the 4th power, 3 raised to the 4th power, minus 6 times 3 raised to the 3rd power. And I get negative 81 right there. So the other point of inflection is at 3, negative 81. And then, definitely what you want to do is look at the graph on a calculator or on some technology that you've got to make sure that what you just found actually agrees with the graph. All right, so let's look at that real quick and go through that procedure. So, all right, so you've got this function, and I don't have the pet function created yet. So what I'm going to do is I'm going to go ahead and clear that function out. And I'm looking at x to the 4th, x raised to the 4th power, minus 6x cubed, raised to the 3rd power. I'm looking at that graph, and you're definitely going to have to kind of do some zooming and whatnot here. So we get a graph that looks like this one right here. I'm going to go ahead and take a picture of that. And then I'm going to go back to my picture here. And I'm going to pick out that picture out of the photos. And there's my graph. I'm going to go ahead and paste that in there. And so what do we get here? Notice that if you look at our graph, look at where it's rising and falling. So you get that the graph, just based on the way this picture looks, what's it doing? That the graph is decreasing until you get to 0. And then it continues to decrease after that. It levels off at 0, doesn't it? And then it continues to decreasing again until you get to, sure enough, 4.5 right there. And then at 4.5, the graph starts to increase. Right, so what do we have here? That the derivative should be negative until you get to 0, and then still negative afterwards until you get to 4.5, and then positive. That's exactly what we got when we looked at the analysis a minute ago. The second derivative, what do we have? That the function, if you look at the concavity of this function, this piece of the graph, the function is concave down until you get to 0, 0. And then, I'm sorry, not concave down, that's kind of embarrassing. Concave up. Let me back up here real quick. So that's concave up right there. That's better. Until you get to 0, 0. 0, 0 is a point of inflection. And then what happens? The graph changes to concave down. And then what do we get? We got that at the point 3, negative 81, right here, you have a point of inflection. And then what happens? The graph changes back to concave up after that, right? So if you're looking at kind of tracing it out, this part in green that I'm putting in right here, this is a place where the graph is concave up. And where else is the graph concave up? It's concave up in this piece right here. Right, and then in the middle in there, the graph in here is concave down, this piece right here. Right, and you can pretty clearly see the points of inflection that you've got in the graph. So the second derivative, its signs ought to go positive here until you get to 0, and then negative until you get to 3, and then positive afterwards, which is exactly what we just found on the previous page. If the second derivative is positive, then changes to negative at 0, and then changes to positive back at 3. So our graph fits in really well with the calculus that we just went through on the previous screen. It's definitely something that you want to check with these problems. All right. Next problem I want to look at, let's look at one more function, I think, and then that will be it for the day. So let's look at problem number 234 on page 411. So this is page 411, number 234. And so we have this function. We have f of x is x minus 2 squared times x minus 4 squared, like that. All right, and so again, we're analyzing where this function's rising and falling, and where it's concave up and where it's concave down. All right, so let's have a look at this. So again, we're going to divide the page up. Let's talk about the derivatives. So a little bit more work. You can multiply all this stuff out. I'm just going to use the product rule to find the derivative. So f prime of x would be the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. Now you're using the chain rule in both cases, but the derivative of the inside piece in both cases is a 1. So f prime of x is 2 times x minus 2 squared times x minus 4 plus 2 times x minus 2 times x minus 4 squared. And then what I would do is I would factor out a 2 and an x minus 2 and an x minus 4. And when you do that, you're left with an x minus 2 in the first term and an x minus 4 in the second term. And so f prime of x would be 2 times x minus 2 times x minus 4 times 2x minus 6 right there. Right? X plus x is 2x, negative 4 is negative 6. You could factor out a 2 right there, and so f prime of x would be 4 times x minus 2 times x minus 4 times x minus 3. Okay. The second derivative, I started a little bit higher up here. The second derivative of that function, now the 4 could just be left sitting out front here, and so then you've got 3 factors in there. So I would just write this out, and in each term I would take the derivative of a different factor. So this is 1 times x minus 4 times x minus 3 plus x minus 2 times 1 times x minus 3 plus x minus 2 times x minus 4 times 1. Right? Each term I just took a derivative of a different factor. The derivative of each of those factors is 1, so that works out okay. So the second derivative would be 4 times, and then you start multiplying all this stuff out. You get x squared minus 7x plus 12 plus x squared minus 5x minus 5, plus 6 rather, that's better, plus 6. And then the last one would be plus x squared minus 6x plus 8. So f double prime of x collecting like terms, finally starting to kind of simplify a little bit. You get 3x squared. Then the x's, you have negative 7x, and negative 5x is negative 12x. Minus 6x would be minus 18x. And then 12 and 6 is 18. Plus 8 would be 26. So let's make sure that that's right. Negative 4 times negative 3 is positive 12. That's positive 6. That's positive 8. And so you get 26. That's right. Like so. All right, so let's look at the critical numbers and the hypercritical numbers. So the critical numbers here, places where the derivative is 0. Since it's factored nicely, that's easy. X equals 2, x equals 4, x equals 3. So that works out pretty well. For the second derivative, I'm not sure, let's see, if that thing factors at all or not. I'm kind of thinking, so that's got to be a 3x and an x. And yeah, the only factors of 26 are 2 and 13, and it doesn't factor. Right, and so because it doesn't factor, to find the hypercritical numbers, you're going to end up having to use the quadratic formula to do that. So we'll do that in a minute. All right, and I'll show you another way that you could do this also. Let's see, you've got f prime right here. We've got 2, 3, and 4, 2, 3, and 4. And so you pick out test values out of each of those intervals. And so you get x equals 0. I always try to use 0 when I can. Between 2 and 3, I might pick x equals 2.5, x equals 3.5, and then finally x equals 5. So when x is 0, you're looking at the factored form at the very end there for the derivative. You get all three of those factors are negative, and so the derivative is negative. At 2.5, the first factor is positive, but the other two are negative, so it's positive there. At 3.5, you get a positive and a negative and a positive, so you get a negative. And then at 5, you get all three factors are positive, and so you get a positive, like so. And so that tells you that the function is decreasing, increasing, decreasing, and increasing, like that. And so you get that f here is increasing, f increasing from from 2 to 3, and then again from 4 to infinity. And then f is decreasing from negative infinity to 2, and then from 3 to 4, like that. Relative maximum, you do have a relative maximum, and that would be at 3. And so you look at what f of 3 is. That's actually not too hard because of the way the original function was written. And so you just get 1 for the y value right there, I believe. And the relative minimums, you have 2 relative minimums, one at 2 and another one at 4. And in both of those cases, the y value is just 0. So that works out well. It also indicates, if you think about the way the shape of the graph is, that this graph's going to have some points of inflection also. And we've got this quadratic over here that's going to give us where those are occurring. Those points of inflection are going to occur. So, okay, so let's see what we can figure out over here. So you've got this function 3x squared minus 18x plus 26. If you want to go ahead and use the quadratic formula, you could find the critical numbers the hypercritical numbers that way. So the quadratic formula would give you x is equal to 18 plus or minus the square root of negative 18 squared minus 4 times a times c, all divided by 2 times 3. We don't really care about the 4 at the beginning. That's a constant factor, and so that doesn't really affect anything. as far as finding these zeros for this equation here. So you have 18 plus or minus the square root of, and then underneath that radical, you have 18 squared minus 12 times 26. So you get that's not too bad. You get 12 underneath the radical right there. And that's all over 6. And so you get x is equal to 18 plus or minus 2 times the square root of 3 over 6. Canceling out a 2, you'd get 9 plus or minus the square root of 3 over 3. So 9 plus the square root of 3 over 3. 9 plus the square root of 3 divided by 3 gives me 3.57 about. So we'll say about 3.6, just to kind of round things off, about 3.6. And then 9 minus the square root of 3, so you have 9 minus the square root of 3 divided by 3, and I get about 2.4. So 9 minus the square root of 3 over 3 is about 2.4. So those are about where my 2 points of inflection are. And if you think about where the relative maxes and mins are and everything, that really makes sense that you're getting values about where we found them. So the second derivative, you have hypercritical numbers at about 2.4 and about 3.6. And so you're using test values, which you might use x equals 0, x equals 3, and x equals 4. So when you put in x equals 0, you're going to get a positive. When you put in x equals 3, and you can go back and verify this, remember, you're looking at the signs of the second derivative. So you're looking at the second derivative evaluated at 3. And what you're going to get there is that that's actually going to be a negative, I believe. Yep. So you're going to get a negative there. And then at 4, you're going to get a positive. And so that tells you where the function's concave up and concave down. I'm going to kind of squeeze it in here so we can get these values in here. So concave up from negative infinity to about 2.4, that's an estimate. And then from 3.6 to infinity. And then concave down from about 2.4 to 3.6 approximately. All right, and then points of inflection. I'm going to let you find the points of inflection, but the points of inflection you're going to get by substituting 2.4 and 3.6 into the original function and getting the y values there. And so I'll let you go ahead and find those values on your own. All right, when you analyze the graph of this function, or when you look at the graph, you definitely would want to look at this and make sure that everything that we've just found agrees with the graph. And probably, again, not a bad idea that I go ahead and look at that real quick. So let's go ahead and do that function also. I wasn't going to, but I think I would really hate to leave it without looking at that graph a little bit more closely. So you have x minus 2 squared times x minus 4 squared. All right, so when I look at that graph, I really want to probably try to stretch this out a little bit. You get a graph that looks something like this one right here. And so let's go ahead and take a picture of this so we can draw on it. And go back to my graph right here. We're going to go on the next page, and we're going to pull that picture off. And just going to paste that in there. Okay, so there we go. And so notice we're getting, sure enough, just like we found or talked about a second ago, we're getting these relative, these 2 points right here at 2, 0, and at 4, 0 are relative mins. The point 3, 1 is a relative max. right? And those are values that we found a second ago, relative max of 3, 1, mins at 2, 0, and at 4, 0. And certainly we have that the function's decreasing and then increasing and then decreasing and then increasing. So if you're looking at the signs of the derivative right here for this graph, the derivative is going to be negative and then 0 and then positive and then 0 and then negative and then 0 and then finally positive again. As far as the concavity, we got that there were points of inflection at about 2.4 and at about 3.6. So 2.4 is approximately right in here, and 3.6 is approximately right in here. And that certainly would agree with the picture right here. That what are you getting? That the second derivative is concave up, and until you get to about 2.6, and that's where the derivative is 0. Second derivative is 0, and then it's negative, and then at about 3.6, again the second derivative is 0, and then positive again after that. So that all fits in pretty well. All right, so that finishes what we're going to do then with section 4.5 in your book. It's possible I'll work another example or two when we come back for lecture next time on Monday. So please be working on your homework. Remember, you have a homework assignment due on Sunday of this week. I delayed the due date on that homework until Sunday. That's when homework 3 is due. I'll be posting homework 2 grades in your D2L gradebook by the weekend. Sometime Saturday or Sunday they should be completed and be up there on there. So be looking for those grades. Please come by for online office hours. Have a great day, and I will be talking to you soon. Thank you very much.